This is the second of the 3 lectures on elements of semi-classical gravity. If you recall, we had talked about essential classical field theory and the corresponding quantization using the classical modes. We had focused on quantization in flat space time, and I had talked about a particular phenomena called vacuum polarization. I had explained 2 specific phenomena which arise due to vacuum polarization, namely the Casimir and the Unruh effects. The Casimir effect arises because of a change in the boundary condition in flat space time, and this can be true in curved space time as well. When you change the boundary condition, there will be a difference between the vacua and the modes in the absence of the boundary condition and the boundary condition, and this difference is some sort of vacuum Casimir effect in a general curved space time. And I had also talked about another important result, which is again a vacuum polarization effect, namely the Unruh effect. I had discussed the quantization of a field, of a scalar field, and recall, for simplicity, most of the time we were considering a scalar field, and often for simplicity we were working in 1+1 dimensions. We talked about the quantization in 2 coordinate systems which cover the same region of space time. On one hand, you have the standard Minkowski quantization, which all of you are familiar with by now, and then we introduce this quantization in a uniformly accelerated frame. And when you have 2 such complete set of modes to carry out a quantum field, they may be inequivalent. I argued as to how they can be related by these transformations known as the Bogoliubov transformations. There were 2 coefficients, alpha and beta, that we need to determine, and I had highlighted the fact that if beta is non-zero, then you have an inequivalent quantization. There, what you had done was you had compared the modes in 2 different coordinate systems, and in particular in the uniformly accelerated frame, when we calculate the expectation value of the so-called Rindler number operator, which was some b dagger b, and you evaluate this expectation value in the Minkowski vacuum, it turned out to be non-zero. Importantly, it turned out to be a thermal spectrum, and as I emphasized, it has close correlation with what happens in around black holes. I will talk about that in my 3rd lecture. This idea of Bogoliubov transformations is going to play an important role in the 2nd lecture that I am giving today, and in this lecture I will cover 3 topics. Something known as the dynamical Casimir effect. The boundaries will not be static, the boundaries will be in motion, and it leads to some interesting results. And then I will talk about the Schwinger effect, and Schwinger effect, as I briefly mentioned in the first lecture, corresponds to production of pairs of particles corresponding in an electric field background, and I will consider the simplest case of a constant electric field, and here I will work in 3+1 dimensions, and then I will go back to 1+1 dimension, simpler case, and I will illustrate what you mean by particle production in a gravitational background. In contrast to comparing the modes in 2 different coordinate systems using the Bogoliubov transformations, what we will do here is compare the behavior of the modes at 2 different times. I introduce the idea of a positive frequency or a positive norm modes. In certain situations they are the same, the definitions match. In certain situations they may not match, and I talked about how one positive frequency mode may not be the same as another positive frequency mode, and there can be a mixture through the Bogoliubov transformation, and that is what happens in a time dependent background. You can define a set of operators at very early times, and you can define a set of operators at very late times, and then you can ask whether there is a mixing of these modes, and this mixing through a non-zero Bogoliubov coefficient beta is known as particle production. Ideally, you would like to calculate the stress energy tensor as we had done in the case of the Casimir effect, but and we had carried out this regularization to arrive at a finite value for the energy density in this closed one-dimensional universe. The regularization procedure in a curved spacetime is much more non-trivial. So I am going to talk about the stress energy tensor only in the first example of the dynamical Casimir effect. I will particularly show that if you have a mirror which is in motion, earlier we had considered a static mirror, now I am going to make the mirror move, and under certain conditions, if the mirror undergoes non-uniform acceleration, what you will find is that there will be a flux of quanta corresponding to the quantum field which will be emitted by this moving mirror, and this idea will be very useful when we discuss Hawking radiations. And there I will explicitly calculate the flux, a particular component of the stress energy tensor, and using the method of regularization that I have already discussed. In the case of the Schwinger effect, I will just calculate the particle number. Please understand, the stress energy tensor or the energy density is a sum over all the energy in all the modes. In the vacuum state, it is simple, it is just omega by 2 or something like that. But when there is time evolution, it will change with time. The energy density at early times can be different from the energy density at late times. But as I said, you need to regulate this integral, and this regularization procedure is more involved in a curved space time. Okay. Therefore, I will just focus on the number of particles produced. If you want to calculate the energy density, you have to sum over all the particle number, over all the modes. So let us start with the dynamical Casimir effect. Well, it is very simple, as this cartoon shows. You have a box with boundary conditions on the field, and you start shaking the box, and it begins emitting photons or whatever the quanta that you are interested in. And moving mirrors can radiate, and sometimes this effect is referred to as sonoluminescence, and there are efforts to actually detect it, and particular trajectories, if you have an oscillating mirror, can lead to higher levels of radiation. How does this arise? As we have done many a time, we are going to consider the simple case of a scalar field, and we are going to focus on 1+1 dimensions, and as we have already discussed, such a scalar field in Minkowski spacetime satisfies this boundary condition. Satisfies this wave equation. Now we need to impose a boundary condition on the mirror. Earlier we had a periodic boundary condition. Now if you have a mirror, you will have to impose a different boundary condition. Typically you will assume the field, for instance, vanishes. That is what, and this is known as the Dirichlet boundary condition. If the mirror is static, it just corresponds to phi at x is equal to 0 is 0. Here you have a moving mirror which is described by a trajectory z of t, and remember we are working in units where c is 1, so z dot is the velocity and it has to be less than 1, and we need to impose this boundary condition on the modes. So how do we go about doing that? Well, one can carry out these transformations. You can, in 1+1 dimensions, you are considering a massless field. It is actually conformally invariant in 1+1 dimension. That is, the action of a massless scalar field is invariant under conformal transformations in 1+1 dimensions. You can show that. And this property allows you to construct the modes. So first carry out a transformation to some u and v coordinates. These are the null coordinates, which are t minus x and t plus x, and introduce a new set of coordinates w and s, through the relations f of w minus s and g of w plus s. And one can show straightforwardly using these transformations that the equation of motion of the scalar field in this ws coordinate system also has the same form. Now somehow what you can do is that there is a trajectory, and you have chosen for the mirror, of course, and you can choose the functions f and g in such a fashion such that s is equal to 0 corresponds to the location of the mirror in this new coordinate system. You can think of a transformation to the frame of the moving mirror, that is it. Okay. And and therefore, this condition essentially corresponds to choosing x is equal to z of t, that is what it is, this condition here. And once you have this condition and you want the modes to vanish on a boundary, okay, what you need is sin omega s. And I have written e power minus I omega w, remember w is my new time coordinate, and these are my positive frequency modes. Or if I invert and write it, I am not interested in the coordinates w and s, I am interested in the coordinates t and x, and therefore, I need to invert them, and these are my positive frequency modes. I presume now you begin to appreciate why I have factors like 2 pi and 2 omega appearing. It is because of the normalization. I have assumed that these come normalized. So, what we are going to focus on is a mirror trajectory where the mirror is initially static. Let us say it is at rest at x is equal to 0 for t less than 0, and then it is moving on some arbitrary trajectory for t greater than 0. And these conditions corresponds to these choices of f and g, and what one can show in summary is the following, that the modes are given by this form, where p of u is given by this expression. Notice p of u is 2 tau u minus u. I will explain what 2 tau u is. There is a figure that will help you understand. Remember, u is t minus x and v is t plus x. So, you have the modes, and p of u depends strongly on how z of t behaves. So, what you have is the following situation here. The mirror is, this corresponds to t less than 0, the mirror is stationary at early times, okay, and it is moving in some arbitrary trajectory at later times. The boundary condition is, it is like a particle in a box. Remember, your wave function is confined to that side, there is no box, there is just one wall here. Okay. So, what essentially happens is that the space time is divided into two domains, one to the left and one to the right, and we will focus on what we have on this side here. So, what happens in this case, modes are coming in and they are scattered by the, they are reflected by the mirror and they go out, and an incoming wave is turned into an outgoing wave. So, once you have the modes, and I want you to appreciate this applies to any trajectory z of t. Another point I want to emphasize is that, notice, tau u minus z of tau u is t minus x. When x is equal to z of tau u, t equal to tau u. So, what it means is that tau u is for a given u, tau u is the time when the wave hits the surface of the mirror. That is what that tau u implies. So, once you have the modes, you can carry out the quantization and you have this structure. The moment you have a boundary, one boundary, the k that we had went from minus infinity to plus infinity in the absence of the boundary is restricted. I have called that as omega, and it goes only from 0 to infinity. What you need to do is as follows. You need to take these modes, right, and you need to plug into this field, and you need to in turn plug it in the expression for the stress energy tensor that we had earlier, and you will arrive at quantities which are divergent. Now, you can introduce an epsilon, okay, some e power minus omega epsilon to regulate the integrals. Remember, the integrals will run from 0 to infinity. Okay, let me just show you what we had done. This is what we had. You will have similar expressions. just that these guys here will also depend on u and v, etc. Okay. Now, you need to introduce an epsilon, regulate the integrals and ensure that the integrals are doable. It is 1 plus 1 dimension, so the integrals will be of the same form, and in fact, and then Taylor expand your result in epsilon. That is all you need to do. Exactly the same thing that you have done here. The integrals will involve that function p of u or its derivatives, and what will happen is that when you remember p contains u, we had replaced t by t minus I epsilon, and therefore, you need to, when you have to take epsilon equal to 0, you may have to Taylor expand u, p of u, and therefore, derivatives of p of u will arise, and you will be left, when you carry out the integral, this divergent quantity, which we will throw out, and what you will be left with is the following expression, is this expression, where p of u, let me explain to you what is p of u. P of u is given by this expression. It is determined by the trajectory of the mirror, okay, and you plug this in here, and you will obtain a non-zero energy density and non-zero flux. And we will talk about a specific trajectory for the mirror, where it behaves like this and accelerates asymptotically, okay, and we will in fact use this to understand Hawking radiation later. What you can also do, which I have not done here, I wanted to illustrate through the example of the stress energy tensor, is calculate the Bogoliubov transformations between the in modes and the out modes, which we will do for the electric field and the gravitational background very soon. Think of the following situation. If you restrict yourself to the time t less than 0, it is just modes are static. So, what will I have? I will have sine omega x e power minus I omega t, that is all. Now, let us say the mirror moves and comes to rest again on some arbitrary trajectory. At later times, once the mirror has come back to rest, what will I have? I will again have sine omega x e power minus I omega t, all right. But the modes in between will be different, okay, and what you can do is that you can try to relate the initial modes to the final modes, or you can try to relate the modes at given time here and any time here through the Bogoliubov transformations. Remember, whenever you have two complete set of modes, I can relate them through a Bogoliubov transformations, and then using those Bogoliubov transformation, you can ask the following question: given that the quantum field was in vacuum state at initial time, what is the number of particles produced by the mirror at later times? Of course, you will be puzzled by where do these quanta coming from, where is the energy coming from? Well, it is given by the energy provided for the motion of the mirror. That is converted, that some of that energy is converted into the particles corresponding to the quantum field. So, that was the case of the dynamical Casimir effect. Let us go on to discuss the Schwinger effect, which is pair production in an electric field. I had briefly mentioned earlier about the importance of these vacuum loops. If you recall, we had calculated the so called Weitmann function in flat space time. Remember how it had looked for the case of a massless field in 3 plus 1 dimension. It had the form 1 over sigma squared, right. On a constant time surface, which corresponds to t equal to t prime, it still goes as 1 over mod x minus x prime squared. And in some sense, that Weitmann function is like saying, given you create a particle here, what is the probability of finding the particle at a given space time point? And what you find is that this Weitmann function is non-zero even on a constant time surface, which cannot happen in quantum mechanics. And that is partly because of these that is because of these virtual pairs that are created and annihilated subject to the uncertainty principle. But what happens the moment I place an electric field? The only thing between the figure here and the earlier figure was that the earlier figure, the time was was along the vertical direction, space was along the horizontal direction. This has been inverted here. Now, what happens when you turn on an electric field? The electron positron pairs may not be, may not come back and annihilate each other. The electric field can, if the electric field is in this direction, okay, then if the electric field is in this direction, it can pull the electrons and push the positrons, okay, and they can actually lead to creation of real electron positron pairs. This is what we want to understand. So, remember here the problem we are trying to study is somewhat similar to studying in a gravitational background. What we have is a classical electromagnetic background. I have two large capacitor plates which has produced an electric field in this room, and I would like to understand what it does to the quantum vacuum. What it will do is that if the strength of the electric field is sufficiently strong, sufficiently high, it will produce pairs of particles. So, we will consider, we need a field which interacts with the electromagnetic field. So, a real scalar field will not do, and therefore, I will consider a quantum scalar field phi, and here I am going to work in 3+1 dimensions to illustrate the standard Schwinger result, and I will consider a massive field, and mu is the vector potential that describes the electromagnetic field, and as you would know, the action describing such a complex scalar field is given by this expression. Please note, we are not interested in the electromagnetic part of the action, because we are not interested in the dynamics of the electromagnetic field. The electromagnetic field is specified to us as I have described here, and it is assumed to behave classically, and we are trying to understand how will the scalar field, the quantum scalar field, behave in this classical electric field background. So, if you vary this action, you will obtain this equation of motion, and I need to make a choice of a gauge, and there is a I am going to consider a constant electric field along, say, the x direction, and I am going to choose a vector potential that gives me the corresponding electric field, and it is easy to convince yourself such a choice of the vector potential will give the electric field. The scalar potential is 0. Remember, it is minus dA by dt will lead to the electric field, and this will lead to a constant electric field. So, now there is a time dependence, because the electric field is a constant, but the dynamics of the quantum scalar field is determined by the vector potential mu, which is time dependent, and that will introduce the time dependence, and that will change the modes with time. The in modes which will behave in a certain manner at early times will not behave in the same manner at late times, and this mixing will occur, and which is what we will interpret as particle production. So, what do we need to do? We need to obtain the solution to these modes in this background. Now, again, a few points which I had emphasized in the first lecture will become evident. Now, remember, if you have spatial homogeneity like we have here, there is just a time dependent background, there is no spatial dependence, and therefore, you can easily decompose your modes as e power I k dot x, and it is only the time dependence that we need to worry about. Another point is that the normalization is not going to change considerably. Okay, there will be a change, and that is a relatively simple thing which we can understand easily. So, we will not worry so much about the normalization as such, we will talk about the mixing of the modes at early and late times. So, what do we need to do? We need to obtain the normal modes and essentially consider the asymptotic forms at very early times and at very late times. There is something non-trivial that happens here. Notice the electric field, since it is a constant electric field, is present at all times. there are no nice asymptotics. It's not that the electric field is switched off at early times, turned on for a finite time and switched off again, which is what will correspond to a realistic situation. If it was the case, what do you expect? You expect Minkowski modes at very early times, Minkowski modes at late times, but the modes will be different because there has been an electric field which has been in between, and you can define positive frequency modes with respect to these Minkowski modes at early times, and you can define a vacuum state at very early times and very late times. Okay. I hope it is already clear to you. If you have such a behavior and you have nice asymptotics, then you can there will be a vacuum state at early times and there will be a vacuum state at late times, and they need not be the same. That depends on the dynamics. So, in contrast here, there is no such nice asymptotics, and therefore, you do not expect the modes to behave to a simple e power minus I omega t form at early times or late times. In fact, they are very complex. You have to be judicious when you try to define what are positive frequency modes. If you have already dealt with some cosmology, you will be familiar with such a behavior. Cosmology often does not permit nice behavior. We will work with a cosmological model where such a nice behavior arises just for illustrative purposes, but for instance when we discuss generic Friedman universes, for instance, you will not always have nice asymptotics. The universe does not permit such nice asymptotic. The scale factor A of t does not go to a constant at early times or late times, allowing you to define nice asymptotically well behaved modes. So, let us understand what happens. All we need to do is that plug this vector potential in this equation and you have something like this, where I presume it is evident this dou t is dou by dou t. And as I already mentioned, there is nice homogeneity, there is no spatial dependence. So, it is clear, this is something I had emphasized earlier, the modes can be written of the form e power I k dot x, and I can and it should also be one thing you have to be careful about is that it will depend on f k vector, not f k. There is homogeneity, but there is a direction, and the direction is set by the direction of the electric field. So, not all k's are equivalent actually, you have to be a little careful about that. So, what happens is as follows: if you plug this in, this partial differential, you are essentially carried out a separation of variables, and the partial differential equation reduces to a total differential equation here, and you have the structure. And notice here there is a kx, while k perpendicular along the ky and the kz directions does not get mixed with the electric field, it is only the kx which does. Now, I need to solve this differential equation. It is not difficult to guess what the solutions to this differential equation would be the what will be the structure. Notice this behaves like let us say I take m squared and k squared to the right hand side and introduce a minus sign all over. Okay. Then what will I have? I will have minus d square f by dt squared minus kx plus qet whole squared, okay, f equal to minus m squared plus lambda squared, or no, plus m squared plus lambda, I am sorry, k perpendicular squared f. Or you can equivalently consider here with these new variables, tau is just a displaced time coordinate and lambda and nu have been conveniently chosen. Now, look at this, take lambda f to the right hand side, okay. So, it will become minus lambda f and I introduce a minus sign everywhere. So, what will I have? I will have minus d squared by d tau squared minus tau squared f equal to lambda f. This is like a Schrodinger equation corresponding to a inverted oscillator. Remember, if it was an ordinary oscillator, you would have had minus d squared psi by dx squared plus x squared psi equal to E psi. But here you have minus d squared f by d tau squared minus tau squared f equal to lambda f or E f. So, you can imagine that it is going to lead to instabilities. Okay. So, you will have, remember how the wave function in the case of the harmonic oscillator behaves at large x. It goes like e power minus omega x squared, something like that. Okay? But here omega is imaginary. So, we expect the solutions to behave like e power plus or minus I tau squared, and that is what happens. The solutions to this differential equation are something known as parabolic cylinder functions, and all these four set are solutions to the differential equation. It is not surprising, you should have two of them, only two of them are independent, the other two can be related to the remaining two. It is just that it is clear from this, if Fk is a solution, Fk star is a solution as well, and that is what happens there. Now, what do we need? You want to understand the asymptotic behavior of these parabolic cylinder functions, and you can look up some standard texts like Gratstein and Reisig, which will list these properties. As tau tends to minus infinity, notice how it behaves like. Okay? Instead of e power minus x squared, it behaves like e power plus or minus I tau squared, because the frequency of the oscillator has become imaginary. And as you can imagine, as tau tends to plus infinity, you have the same behavior. Now, what do you need to do? You need to impose initial conditions at very early times, which means you need to choose a positive frequency mode, a mode which behaves like e power minus some I omega t as t tends to minus infinity, but that is simply not possible here. So, you need to make a judicious choice, and what one finds is that, notice it is, if you look at d nu of minus 1 minus I tau, okay, look at this, which one is this? It is minus 1 minus I tau, let us look at that, it is this guy. It is e power I tau squared, but you need to differentiate the phase and take tau equal to minus infinity, and therefore, this will behave like a positive frequency mode at early times. I hope the point is clear. The frequency is changing with time, you have no choice. So, you need to define the vacuum in the best manner possible. You need to choose something which behaves positively at very early times, and that happens to be this mode. So, in other words, you can decompose your quantum field in terms of this modes plus the complex conjugates, Hermitian conjugates. And now, what do we need to do? We need to understand how it behaves at late times, and that just emerges from the properties of the parabolic cylinder function. Okay? So, what you find is that this is the positive frequency mode at early time, and therefore, this is the negative frequency mode, and this is the positive frequency mode at late time, and therefore, this is the negative frequency mode. And what happens is that if you start with this mode and define the coefficient of this positive frequency mode to be the annihilation operator, and the vacuum state to be that state which is annihilated by that annihilation operator, you have a vacuum state, and you are working in the Heisenberg picture. So, therefore, the vacuum state does not change, the modes change, okay? And the change in the modes can be easily arrived at in this manner. So, now notice you have a positive frequency mode which is here at early times. This is your positive frequency mode at late times, and this is another, this is the negative frequency mode. So, what you have done is that you have taken one mode and have written it as some alpha times something plus beta times another, right. All I am doing is that using the Bogoliubov transformations that I had earlier. Here it is simple, it is the same, they are described by the same wave number. Earlier I had an I and a j. It is the same wave number k which determines all the modes, behavior of the modes. All modes evolve independently, there is no mixing, it is a free field. And therefore, just from this property of the parabolic cylinder function, it is very easy for me to determine what is alpha and what is beta. And where lambda is given by this expression, remember lambda is given by this expression. There is no kx that is present in lambda, it is only k perpendicular, which is kx and I am sorry ky and kz, and the mass which appears. And remember, if you try to calculate the number operator, so I can define a set of B, I can define an annihilation operator with respect to this positive frequency mode. I can define an annihilation operator with respect to this positive frequency mode, which happens at late times. Now I can ask the same question that I had asked earlier. If I calculate the number of particles produced at late times in the in vacuum, that will essentially be given by the modulus of the beta squared, okay, and that can be easily calculated, and it is given by this expression here. And another important result which I did not discuss is this guy, that modulus of alpha squared minus modulus of beta squared is 1. Remember, when you have two complete set of coordinates, I can relate one set of creation and annihilation operators to the new set of creation and annihilation operators through the Bogoliubov coefficients, but both these sets of annihilation and creation operators should satisfy the commutation relations, and it is those commutation relations which will lead to a result like this. So this is essentially the Swinger's effect, and what you say is that this constant electric field background produces so many particles corresponding to the quantum field, and importantly this is completely non-perturbative. Notice, as E tends to 0, you expect the number of particles to go to 0, but it is not. It does go to 0, but it is in a very strange manner. It goes as QE tends to 0, notice it is e power minus 1 over some quantity which goes to 0. So it goes to the coefficient, the argument of the exponential goes to infinity, and therefore the exponential goes to 0. So it is a truly non-perturbative effect. The last of the phenomena I am going to study is particle production in a gravitational background, and this is expected to happen in any Friedman universe, but because of the lack of nice asymptotic behavior that you often have in asymptotic universes, I am sorry, in Friedman universes, it is difficult to define what is a particle in general Friedman universes. But in this particular problem I am going to study, there is nice asymptotic. In that sense, it's a simple and somewhat artificial Friedman model. Again, I am going to go back to 1 plus 1 dimensions, but I am going to consider a massive field in contrast to a massless field that I have discussed earlier. This is the Friedman metric. I presume all of you know about it, and A of t is the scale factor. And as you know, you can write, of course, we are working with a spatially flat Friedman metric, and as you know, you can introduce something called a conformal time coordinate through this relation, in terms of which it is called the conformal time coordinate, because in terms of this coordinate eta, the Friedman metric is conformal to flat space time, and this conformal factor we have conveniently chosen as C of eta. And I am going to work with this choice of C of eta. Of course, it does not describe our real universe, it is just mathematically convenient example to illustrate the idea of particle production in a gravitational field. So the universe expands essentially from A minus B to A plus B. As I mentioned, I am going to consider a massive scalar field in a Friedman universe, which is described by this action. Again, our goal is to understand the number of particles produced by this background, and therefore I am going to just focus on the behavior of the modes. I need to solve, given I have everything given. I have a massive scalar field, I have the A of eta, more precisely the C of eta given to me. I just need to solve for the modes, understand this asymptotic behavior. and relate the modes at early times to the modes at late times. That is all I need to do. And importantly here, this has been introduced because of reasons I just mentioned. There is nice asymptotic. It is Minkowskian at very early times, it is Minkowskian at late times, but this is different Minkowskian from that Minkowskian. So, this is the equation of motion of the scalar field, and this is something we have encountered earlier. And what you do is that you substitute this Friedman metric that we had in the previous slide in this equation, and you will arrive at an equation like this. I had mentioned that 1 plus 1 in 1 plus 1 dimensions, massless scalar fields are conformally invariant, and that is well illustrated by this example here. Notice if I just switch off the mass, if I set mass to equal to 0, I am left with the wave equation, simple wave equation that I would have had in the Minkowski space time. It is just that t and x are replaced by eta and x, okay. And in which case there will be no particle production at all. My mode will be e power minus I k eta or minus I omega eta, and it will remain as it is if there is no mass, and there will be, it will be a trivial behavior. So, I can decompose the modes because there is time, spatial translational invariance. I can decompose the modes in this form, and this chi k satisfies this differential equation. What I just said will be evident here. If I set the mass to 0, chi k solutions are just exponentials, and therefore, there is no non-trivial evolution, and it is the presence of the mass that affects, that takes into account the effect due to c of eta. So, I need to solve this differential equation, and I need to, evidently it will have two solutions. I need to choose a solution that will behave nicely at very early times, which mean I need solutions of the form e power minus I omega eta at very early times. What one finds is that the solutions can be written in terms of hypergeometric functions. We are going to choose the solution which behaves in the required fashion, and that solution happens to be the following. Okay. It is like, if you go back to the potential problem, Schrodinger equation problem, this is like scattering in a potential. Remember, c of eta in a step potential, and the solutions happen to be hypergeometric functions. If you ask for the exact solution, it is given by this. There are two solutions, and we have chosen all these constants in a suitable fashion such that as eta tends to minus infinity, it has this form, where omega n is given by this expression. Notice, as eta tends to 0, this becomes a minus b. As eta tends to minus infinity, this becomes a minus b. C of eta becomes a minus b, and as eta tends to plus infinity, it becomes a plus b. So, I can define an omega in, which is k squared plus m squared a minus b, and omega out as k squared plus m squared a plus b. That is what I have here, omega in, omega out, and there is omega plus or minus, which is essentially the sum or the difference of the two omegas at early and late times. So, what I have done, I have chosen this mode which at early times behaves as a positive frequency mode. Now, all I need to do is look up Gratchen and Reisig, and it will tell me that, it will give me a relation between f in terms of two other f's, okay. And you can ask what is the mode that behaves in the positive frequency mode at late times, and that happens to be this f, all right. And there is a difference between omega plus is replaced, omega minus is the same, all right, but omega in is replaced by omega out, otherwise everything behaves in the same manner here. And it is this guy which behaves in this fashion at late times. And you can ask what is the relation between this and this. This is where I go to Gratchen and Reisig and understand the relationship between the two, and you can obtain this relation very easily, okay. Clearly the modes uk in and uk out are not equal, remember these are positive frequency modes. If it had remained the same, then there will be no Bogoliubov coefficient beta. Okay, it will have been 0, but they are not the same, and therefore there will be a non-zero Bogoliubov coefficient beta, and you can show that the UK in and UK out are related through a beta in this fashion, and beta is non-zero, and it is given by these expressions where these gammas are the gamma functions, and again this just follows from the property of this. Remember, you would have carried out this scattering problem in quantum mechanics with a step potential like that. Okay, it is very easy to solve. If you smoothen the step, you will have a tan hyperbolic function. The solution happen to be much more messier, and they can be, but you know, all the properties of hypergeometric functions are well understood, and you can easily derive this result. In some sense, beta by alpha mod squared is like your tunneling probability. I will let you understand that in that language. Okay. And of course, you know, this is the number of particles produced mod beta squared, and again it is trivial to establish that they satisfy this condition. And another thing to notice is that, notice what happens. Remember, omega plus and omega minus are the difference between, or the sum and the difference between omega in and omega out. Notice omega minus is omega out minus omega in by 2. When omega in out equal to omega in, this guy vanishes, beta is 0. It just corresponds to A equal to B, which means you just have purely Minkowski background, and therefore there is no non-trivial evolution. And this quantity mod beta squared represents the number of particles that are being produced at late times in the in vacuum by the time dependent gravitational field. We will come back to discussing the time dependent gravitational field when we start in the third lecture, when we discuss about the perturbation spectrum associated with the quantum field in a de Sitter universe. And I will this is with this I conclude my second lecture.